Thank you very much. Thanks everyone for being here. My name is Brian Pauw. I have been trying for the last 12 years to get the perfect data correction method going. And I'm happy to say that with the help of our colleagues at the Diamond Light Source, we now have a complete and automated solution that will do this for you, which we will demonstrate. Now, as Nicholas said, I have been around the world. I am originally from the Netherlands, but I've been in Denmark, in Japan, and now in Germany. Nowadays, I work at BAM. BAM is the German Federal Institute for Materials Research and Testing. It is essentially the German counterpart of NIST, although perhaps not as big or not as well known, but its mission is still the same. So at BAM, we try to support academia and industry with all their materials research questions. That means that we are trying to provide, that part of our mission is to provide reference materials, but also reference methods and reference data. And it's in particular for these last two that data corrections is very useful. Now, as I said, we've been doing these data corrections, we've been developing these data corrections, and I wouldn't be standing here if I didn't test them. We have tested these data correction on a very wide spectrum of samples. This has been tested at the I-22 beamline at the Diamond Light Source for the last 1.5 years with the samples that have come over their floor, and is also done in our own laboratory with researchers from BAM, as well as researchers that we collaborate with. So, as Nicholas said, we are very happy to collaborate with everybody who's got interesting materials. This is interesting for us because we get involved with all these nice materials research projects. And at the same time, we can try out our universal data correction method to all of the materials that they bring into the world. So this was helped by the fact that I was allowed to buy my own instrument or to have my own instrument built to my quite exact specifications. As Nicholas said, it is a heavily modified version of a Xenox Zeus 2. It has two X-ray sources, copper and molybdenum. It has a nice collimation section with 3 sets of scatterless slits. The third one is inside the cowling there. It has a very big vacuum sample chamber that allows us to load a variety of sample environments. And together with my colleague, Dr. Glenn Smales, we are taking care of all the samples that we get in. One nice feature in this machine is the detector. It is a relatively small Eiger 1M. It's about this big with the detection surface. And this detector sits on a motorized platform, so we can drive it into the sample if we're not careful. We can drive it very close to the sample if we are. And this means that we can collect the wide-angle scattered region, also including the X-ray diffraction peak. We can even, with a molybdenum source, we can get a Q range so wide that total scattering and PDF comes into question. But we haven't started looking at PDF just yet. So the data collection is in 2D. The data corrections are also all done in 2D. So if you have texture or orientation in your sample, then you can get a nice corrected scattering pattern in the small and the wide angle regime in 2D, and then you can let your two-dimensional fitting algorithms loose on this. Anyway, so we have a moving detector. That means we can detect crystalline materials in the wide angle regime. And when we move the detector further back, we can then detect the smaller scattered angles. And this then gives us a more comprehensive insight on the materials that we measure. In this case, the sample was a sample from one of our colleagues from Birmingham University. This is a porous carbon support with iron carbide nanoparticles in it. So the information content in these X-ray scattering patterns are in essence a length frequency map of your sample. So it shows you all of the characteristic length scales of the contrasting objects inside your sample. that includes, if you look at a wide angle, that includes things like crystal lattices, and then the smaller the angle you're measuring at, the larger the structure you're measuring. So in this case, we're also measuring the whole nanoparticles that are embedded inside. And at even smaller angles, we're seeing the length scales and the structure of the carbon support of this. Note, however, that in principle, when I say contrasting objects, it means anything with an electron density contrast, whether or not it's regular. So for things like crystal lattices, you have lengths which appear very often, and that's why you get these very nice diffraction peaks. But even for completely amorphous materials, if you have an amorphous nanoparticle in solution, you would still see an X-ray scattering pattern. You'd be able to derive from that what the size distribution is and what the volume fraction is of these particles that are floating around in your dispersant. The difficulty with X-ray scattering is, however, that we don't have these nice peaks. So the information is usually, well, not usually quite as flat as this, but is usually quite featureless. The information content is quite low. And so you can do your data analysis on X-ray scattering data, and you can get your size distributions and volume fractions out, but you can do this for good data and get good results out. You can also do this for bad data and get bad results out. I mean, garbage in, garbage out. However, there's nothing to show that your data corrections haven't been sufficiently accurately done. So it's important for the researcher to do the data corrections to a sufficiently high level that these analyses give the right answer and not just any answer. So that means, in most cases, that we want to fit a scattering model to data, and that, of course, works best if you bring these two as close together as you can. That means that for the model, you want to account for reality. That means including things like beam smearing, beam divergence into the model can be a big step towards matching your data. Likewise, for the data, you want to correct this for any imperfection that you have during your measurements, or at least as far as you can do this. Now, this is quite a problematic topic to research. And you can see this when you try to get funding for this. If you go to a funding agency and you say, I want to study data corrections and get really a complete set of data corrections, the first thing they say is, well, it's not really groundbreaking research, is it? And it's not like you're going to cure cancer just by having good data. Well, opinions might differ over there. The second thing they say is, well, X-ray scattering in one form or another, whether it's X-ray diffraction or small angle X-ray scattering, has existed for more than 100 years. Surely somebody in the 60s or 70s has sat down for a couple of years and solved this problem. So basically, isn't it solved? Well, let's go to the library and find out. In the library for data corrections, you will find a very wide spectrum of information on data corrections. And this is just a cross-section from my library. I didn't take particular attention to lift out anything specific. Here you can see, okay, you can get corrected data by subtracting a background from your sample, and you're done. There is this one, which is almost the same, except that they take a volume fraction of the analyte into account. That's already a step better. And then you look at the neutron scatterers, and of course they did everything better earlier. They have got a pretty complex data correction equation, and what I like about this is that it also propagates or it also calculates the uncertainty estimate on your data. And the uncertainty estimate I really like because that really tells you what the value of your data is. Your intensity doesn't really do that. This is also why in the data corrections that we're proposing, we are actually propagating all of the uncertainties through all of the data corrections so that you can have your data not only on absolute scale but also with uncertainties attached. Many people just use text to describe their data corrections, so they say things like, well, we just use whatever was available at the beamline, which is in principle fine, except that I then need to go and look at what the beamline does to find out whether I can trust their data or not. This one worked quite nice, which I have, which I regularly cite. They try to get a good small and wide angle scattering pattern for water. And they removed background scattering, direction-dependent absorption, geometric corrections. They did some more angular variation corrections, and removal of the Compton or incoherent background. And this is the first paper where I really see people, for X-ray data, to subtract the incoherent background. And this one is also one of my favorites because this one brings your data in absolute units. But from taking a look at this cross-section, you can not really get a good idea about which one of these are right. They can't all be right. Some of these are conflicting. So some of them must be right and others might be less right. You don't know what assumptions were made for these. In many cases, they're not specified in the text, but people are usually looking at only a small field, only small angle scattering, or only wide angle scattering, or only X-ray diffraction, or only neutrons. So there are some implicit assumptions made in that which aren't always clear. A beginning materials researcher doesn't really know what is important for their materials. They can then try and find somebody who did X-ray scattering using the same materials and try to follow their data correction procedures. But there's no guarantee that they did their work properly. So that there's no guarantee that if you just progress along the fields that you will get the correct data. So in conclusion, what a mess this is. The first time I saw this was during my PhD, and I thought, okay, that's kind of confusing. I did my data corrections, and then I did my analysis, and then I wasn't sure whether the data was correct, so I redid the data corrections, and this whole loop repeated itself a couple of times. Now, when I was in Japan, I thought, okay, that isn't really productive. Can we maybe just do everything? So this, of course, means that we need to find out what everything is. So I wrote a paper called Everything Sucks. This simply lists all of the data corrections that you can do. There's about 18, 19 in this paper. And many of the data corrections aren't actually all that difficult. It's just usually normalizations that you do. There are a couple which are more complex, such as the self-absorption correction and the polarization correction, but they're not overly complicated to do. There's just quite a few of them. So can we maybe just do data corrections right and do it just once? In order to answer this question, we figured out a complete methodology to put all these data correction steps in the correct order in a universal data correction sequence. That would allow you to correct any data for any sample and get the best results out. And of course, we automate this because I don't want to sit and do these things by hand. Now, I do have a little demo. Let me just make this one small and bring up the other one. This is Dawn. This is the data correction package which is made by the diamond light source. It's made for a wide variety of their beamlines. It can do data processing, and at the moment it's still empty. So I will bring up the files that I need for this. Oh, not that one. No. Yes. Okay. Good. I'll bring up the files that I need for this. One of these is the pipeline. It's the sequence of corrections that I want to have done. I can load that in here. These are all the corrections in sequence. I can then load up my data in here. It will ask me what data do I want to load. These Nexus files contain quite a bit. I want to load that data, and then I am done. Right? That's it. I've got my data over here after the last step in absolute units. it's corrected and actually does have uncertainties associated with it. They're not shown at the moment. But it has gone through all of these steps. And while this is only a visualization, there are multiple frames in this image, it doesn't take that much longer to actually do all of these corrections and store the final result. So if I press OK, it just does all of these corrections and it stores the final result in another Nexus file alongside with a copy of the original. So that was easy. Let me go back to my presentation if that comes up. All right. So what does it do and what are the requirements for this? Well, let's take a look at one of the easy cases. If you have an analyte which is present in your sample at volume fractions of less than 1%, then I'd say you have an easy case. In that case, you can measure your sample, which is usually an analyte dispersed in something, inside a container. From that, you would subtract for your background the container. Oops. You would subtract the container with the dispersant in it. Now, this dispersant has to be as close as possible to this dispersant. So if it is a buffer of any sort, then please measure that buffer. Even water can be different depending on how hard it is. And then it does you do all of these corrections. Now, there's a table in our paper. There's a diagram in our paper which shows this in a little bit more visually pleasing way. But essentially, I have my data correction steps over here. I do this series of steps until here for both of the measurements, so for my background, which is cell and dispersant, and for my analyte in the cell and dispersant. And then at some point, I say, I correct this, I subtract my cell and dispersant from my mixture, and then I will have my analyte out. I do a couple more corrections, and then I'm done. However, to make it truly universal, we can't make this assumption. We can't make the assumption that the analyte is there in a low volume fraction, because especially geologists like to study things at high volume fractions, and that's where things get a little bit more tricky. In that case, you need to separate your background in the background from the cell itself. That doesn't change. But the amount of background of the analyte that you subtract has to be reduced by the volume fraction that your analyte takes up. You know, everywhere where your analyte is, your dispersant isn't, so you're not seeing that signal from that. And in this way, you can go up to very high volume fractions as well. What you do in that case is you do your data corrections, well, in 4 columns. In 2 of these columns, you have your cell background. In the one case, you have the dispersant in the cell. In the other case, you have the analyte in the dispersant in the cell. And you'll notice that at the end of the first column, you have your dispersant signal in absolute units with uncertainties. And that can be quite useful. If I use chloroform as a dispersant, then I now have that chloroform signal. I can store it in a library and use it later on that I have a sample in chloroform. That means I don't need to measure them every single time that I have this particular dispersant. Now, at the very end, you then correct your dispersant for the displaced volume of your sample, and you subtract it from your analyte, and then you have your analyte over there in absolute units and with uncertainties. Note that the azimuthal averaging, what brings it into a one-dimensional curve, is optional. So if you have 2-dimensional data, you stop here. And then you have your 2-dimensional data in, as I said, as good as it gets. Now this is just 2 examples. We have in our paper, in table 1, we have a list where we clarify what background you need to measure for all of these samples. In case you're measuring solid dispersions, powders, liquids, and gases. We're not doing plasmas just yet, but that should be pretty close, maybe. So what doesn't it do? There's a couple of things that it doesn't do because we haven't gotten around to it yet. There's a couple of things that it doesn't do by design. So let me talk about the last one. There's a couple of things, one of which is beam smearing. Beam smearing, taking care of the beam, the finite size of the beam and the divergence of the beam, is something that in principle you can do to your data. You can try and de-smear your data for your beam profile. And some do, but this is a mathematically ill-posed problem, and it is a risky thing to try because you will increase your uncertainty estimates, and you may introduce artifacts into your data. It is, however, much safer to take the beam smearing into account in your model, and thereby improve the match between the two, because here it's just a convolution with the model with a known beam profile. Same goes for multiple scattering, multiple diffraction. We might be able to indicate whether this is an issue during the data correction step, but we can't or we won't correct for it. You can calculate this much better in the model itself. And then there's a Lorentz correction. This is common in X-ray diffraction. It's the efficiency correction for crystal lattices at wider angles. This we haven't included because it's only valid for regular structures and not for amorphous structures. And therefore, you should correct your diffraction peaks with the Lorentz correction in your model, but leave all of the model information for the rest of the structure uncorrected for this. There's a second reason why we don't do this, and that's because if you do this correction, your data tends to infinity at zero angle, and that's not something we can live with. So what doesn't it do yet? Well, we will calculate an automatic X-ray attenuation coefficient and a scattering power calculation, so that you've got your scattering power, that's nice, but also you can include the incoherent scattering. This isn't a big effect in X-ray scattering. In fact, most people just neglect it, and they're actually pretty correct in doing so. However, by including this, we may be able to get this data correction procedure applicable to neutron scattering and neutron diffraction as well, which would be kind of cool. We will do an automatic thickness calculation. In particular for powders, this is very important because you don't know how densely you've been able to pack your powders. You don't know how fluffy your particles are. So by knowing the X-ray attenuation coefficient, we can calculate the thickness and correct for this. We've done this by hand, and this works. And we can automatically detect and flag possible problems. This is particularly useful for the users, but also for us, so we can find out if there might be any issues with your data that we need to take into account. All right. Now, as soon as I finish the data corrections, I figured that I need some values for this. You can't do a transmission correction if you don't know the transmission. So then I needed to develop a good way to measure everything. This, of course, needs to be stored together with the data itself, so we are heavily relying on the Nexus structure for the data format. So I can go back to Dawn for this, because I can actually show this. It should have automatically loaded, but I forgot to click the text box. Right. So in our files, we include the Nexus structure that is that's included in the DECTRIS files, but we include a little bit more. So here we have our process data. This is after the data correction. We have, of course, a result for this, but we also have documented the entire process that we use to get there, each processing step with its own parameters. So we can recreate the entire data correction automatically. In the raw data itself, we've got information on the instrument, on the proposal, and on the sample. So we have information on the beam flux at this point, the beam wavelength. We've got information on the thickness, and soon also on the composition of our sample. The instrument contains more information than you will ever want. This, in detector 00, has over here the section that comes out of the DECTRIS files with information that some of which I don't even know what they are. But it's probably good to have this information in there just in case we're noticing something odd with the data, and we need this. All right. So that Nexus structure is pretty cool. And I can get back to my presentation. Yeah. So that Nexus structure is pretty cool and helps us very, very much. So around this, as I said, we've created a methodology. This starts with a sample sheet. Users have to fill in a little bit about their project, a little bit about themselves, but also information on the samples. And this includes an atomic composition or an atomic composition estimate and a density or a density estimate. The more they provide us, the better we can help them. This goes into the electronic logbook. In the electronic logbook, we define our measurements, how many repetitions are done, which configuration do we do it in, or configurations, what is our background, and so on and so forth. This gets converted into a spec measurement script. So this way, we're sure that the information in the electronic logbook is correct, because if you don't fill this in correctly, you do not get your measurement script, and it will not do your measurements for you. If you do fill this in correctly, you're done. You can go home, because these measurements will run automatically over the weekend or over the holidays. We've done plenty of those. In a variety of configurations with different X-ray sources and with racks and racks of samples. We then collect all of our files. This is about 5 files per measurement. We pack these all together in this big Nexus file. We feed in information from the electronic logbook and from the sample and proposal sheet. And then we can do our data corrections. So this was developed over the last 1.5 years because we wanted to do this. This can now be done automatically. We don't need to look at it. It runs headless in the background. After this, finally, you get to do your analysis. And we hope that all of this will be transparent to the user and that they don't need to worry about this and that they can focus on what is important to them, which is get the structural information on their samples. We're also packing this into SciCat at the moment. This is a project run by the European Spallation Source and the PSI, as well as Max4. It is a data catalog or a measurement catalog, which we're now trying to develop. All right, what are the results? Well, I've taken some results from the materials that we've measured so far. This list was up to date until, I think, March, but it just shows the spectrum of materials that we measure. So we measure composites, we measure simple particles like titanium and zinc oxide. We measure rubbers and resins, and I think DNA is also in there. That one wasn't so easy to measure. But this then stands together with the samples that they've measured at I-22. One example is that of a background subtraction. These are samples from Vittorio Saggiomo from Wageningen University. He has gold nanoparticles embedded in PVA, which he can then 3D print. Of course, from that, we need to subtract a background of clean PVA, and these are not the same thickness. So this is the data from the gold nanoparticles in PVA. This is the PVA itself, and then we can subtract the two from one another. You see, it works pretty well. Now, this is not magic, however. So slight variations in your flux or your transmission or your thickness, if there's even a little bit of uncertainty over there, you get an imperfect background subtraction, and that's why you get still some features over here. But I'm still pretty happy with the results that we got. Wide range examples are also some of our favorites. So as I said, we can move our detector at different positions in our camera. And this is done in a motorized way, so we can easily do 6 positions without breaking a sweat. And what you'd normally do in these experiments, if you have multiple detectors or if you move your detector around, is you take your two data sets, you find a scaling factor, and then you decide on a point where one data set is not good enough anymore and the other one should start. We don't have to do this anymore. All of our data sets are in absolute units, so this is the way it comes out of the machine. They all overlap automatically. And now we have a data merging script which merges these data sets taking the uncertainties into account. So if you have data points with a very small uncertainty, so very good data points, they're weighted much more heavily than data points with a large uncertainty. And in the end, you get a scattering pattern like this. This, by the way, is the tobacco mosaic virus, which we measured, I think, 2 weeks ago. We have some interesting things with multiple energies as well. So we have two X-ray sources. We usually try both of them. Usually they give us the same result, except that copper goes a little bit lower in Q, molybdenum goes a little bit higher in Q, but they usually overlap, except in this case. So here we had a ZIF8, which is a metal organic framework, which shows nice crystalline peaks, and these are all the same, but the background is different. And that's because the zirconium in the ZIF8 fluoresces a little bit. So it increases the background for the molybdenum source and not for the copper source. So in this case, we have a little bit of information, fluorescence information about our sample as well. The complete data set looks like this. We have corrected it, of course. In this case, we subtracted the tape background. We use the same Scotch magic tape that everybody uses. Sandwiching our powders in between, and this is the signal from that. So the correction isn't big, but your peak profiles actually become a lot better, especially at the lower intensities. Here's one from I-22. This is for wide-angle corrections. Here, some geologists were synthesizing a crystal in situ in solution. This is the way it comes out of their detector. Somebody put in a very large crystal and broke one of the panels. But on the whole, it looks quite good. This part is missing because that detector had a bit chopped out of. So behind this sits the small angle scattering detector, and this is then the wide angle detector. They then subtract their beamline background, which includes two Kapton films and a bit of air scattering. And if you do that, you see that this one is missing. These are the Kapton peaks in the middle. And then you can subtract the cell and the solvent, and then you're left with this. And the contrast isn't very high over here, but I hope you can see just how far out you can now see these rings. And these are very clean peak profiles that you can immediately analyze. So much more useful. It's much more useful to do this than any sort of rolling ball automatic background estimation. All right. So that brings me almost to the end of my talk. What do we do in the future? Well, we will push hard for adoption. Now that the whole thing is developed, we're convinced that this can benefit a lot of beamlines, a lot of lab instruments, and we're hoping that we can convince people to really implement this. Of course, this isn't easy because scientists are a super conservative bunch. And once they've implemented something at their beamline, there must be a very good reason, or it must be very easy for them to change anything. That's why, while the data corrections are now programmed in Java, we will refactor the thing in Python. We will refactor this as a Python library, so without the graphical user interface, so that any beamline can load up the library, load their Nexus file, and just do whatever data corrections they want in whatever order they want. Of course, our work is never done. We will still push for completeness, and for universality. I hope to include the neutron community in this as well. And there's a couple of things that we don't do yet. So count rate and flat field are still taken care of by the detector. Before we get our hands on the data, this is something that we want to take out. In particular, because of the uncertainty estimates. The uncertainty estimates should be calculated on the actual detected photons and not on the corrected photons. So we should calculate them before we even do the count rate correction and flat field correction. And as I said, there's another problem with adoption, and this is the analysis software lag. I've been trying to convince my friend at the Powder diffraction beamline to adopt these data correction strategies, because I think it would be a great benefit for them to be able to subtract their cell and their instrumental background. However, she says, well, the users aren't asking for this. And even if they, I mean, the users probably don't know what to do with a big Nexus file like that, with data in absolute units and with uncertainties. They want 2-column or 3-column ASCII data. On top of that, the analysis software doesn't support it. So even if the users would want it, the analysis software, in particular for X-ray diffraction, often still requires you to load up 2 or 3-column ASCII data, and maybe even with the intensity normalized to 100 for the largest peak, because that's what Fortran used to like. So that needs to be fixed before this even can be of any use to them. All right, and then I hope that we can get on with life. Well, not me probably, but but the material scientists can get on with life. They want to use scattering in any of its forms to help understand their materials, and so it's much easier for them if they don't additionally get saddled with the data correction problems, if they can just rest assured that at least their data is absolutely correct, and that all of their problems lie in the analysis of the data. So that's it for my talk. I would very much like to thank everybody who's been instrumental to the last 12 years. I've probably missed out quite a few people here, but it's an okay cross-section. And I'd like to thank you all very much for your attention.